Yeah, I'm ready.
Right. So welcome to the last day of the workshop. So our first speaker today is Eischen, who will be talking on Beyond Hilbert Modular Forms and Hilbert's 12th Problem.
Thanks, Jean Kopp. Especially Jean, and I'd like to thank the organizers for inviting me to speak here. This has been a really excellent conference, modulo the fact that lots of people are falling sick. The talks have been great, and I've been getting a lot out of it. And I've also really enjoyed the location. It's my first time in Edinburgh, and it's been really amazing. And I'm really glad that I get to be here at another conference in 2 weeks. So I asked the organizers what they were hoping I would speak about here. And they said they were hoping I'd speak about how some of the ingredients, in particular p-adic Eisenstein series, extend beyond this, the setting of Hilbert modular forms and Hilbert's 12th problem. And those extensions extend pretty far and constitute significant breakthroughs beyond this one. And so I want to talk a bit about that. So just earlier this week, for instance, in Mahesh Kakti's talks, we saw p-adic families of Eisenstein series whose constant term is a Hecke L function attached to a Hecke character for a totally real field. And maybe we had something like a 1 minus k in there for some integer. And I think he used Blackboard bold psi. I'm just going to use chi as I have it. This is a bit totally real field. And in this talk, we'll be looking at an extension of this. So in particular, the constant terms aren't necessarily going to show up like that, but we'll be looking at certain p-adic families of Eisenstein series beyond this setting. And just I just noted we're not really going to see the constant term there, but the reason that we're looking at these still comes from p-adic L functions. So in particular, well, just more generally, even forgetting about p-adic for a moment, we have, if you want to just look at, say, big box of properties of L functions, but probably for most people here, those are, if you care about this, algebraic or p-adic, but you could also look at analytic things. And at least in certain favorable settings, if you want to study these, a good place to go is to a collection of properties coming from associated Eisenstein series. So I should say properties of certain L functions. So properties of certain Eisenstein series. So we have various recipes in the middle here. For instance, one of them comes from looking at constant terms. That's kind of the simplest way this might happen. But there's also other things. There's a Rankin-Selberg method. If you look at Katz as an extension of the work of Deligne and Ribbit, where you have a Hecke character of a CM field. There he uses something called Damerel's formula. There's something called the doubling formula. So there's various recipes. The ... These are all going to at least be mentioned in the talk. The ones here, the dot, dot, dot is just that there's more out there, which is not going to be mentioned explicitly in the talk, but just be aware this is not a complete list. It's an actively growing list. This is an active industry making these recipes that take in certain Eisenstein series and other automorphic data and output L functions. So why, maybe you might ask then, like, why do you care about moving over to this box in particular? P-adic properties of certain Eisenstein series imply p-adic properties of certain L functions. And so why do we want to do this more generally instead of just stopping at Hilbert's 12th problem? Well, for instance, we have Iwasawa theory, which we heard about in Yukako Kazuka's talk a few days ago. We heard about, there she is. We heard about non-commutative Iwasawa theory, for instance, and one of the star players in the main conjecture is a p-adic L function again. So there's lots of motivation to try to understand p-adic properties over here. And one of the main tools that we have for that, at least for interpolating values, comes from automorphic forms, and in particular Eisenstein series. So that's why we're interested in this extension. So before we get to the extension, though, I just want to actually yeah. So I want to just go back to the first instance for p-adic properties. So first instance of this phenomenon for the p-adic setting. And this goes back to Serre. So in the 70s, or published in 1973 in the Antwerp series, it's in volume 3 for people who care about this. He has an extensive article putting modular forms into p-adic families. He proves a bunch of things in there, and among other things, he proved that, for example, just to give one thing that's useful in the context of what we have on the board so far and where we're headed, he proved that if you have, say, two modular forms, f of q with q expansion a naught, a1 plus a1q plus a2 q squared plus dot, 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 and g of q equals b naught plus b1q plus b2 q squared plus dot, 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 dot. If these are modular forms with p integral coefficients, and be careful here, p minus 1 doesn't divide their weights. They need not be the same weight as each other, but they can be different. But we're going to put an assumption on the weights. Then if an is congruent to bn mod p to the m for all n greater than or equal to 1. So here, just throughout the talk, as always, fix a prime p, and m is just a non-negative integer here. So you're working on some power of a prime. Then in fact, a naught is congruent to b naught mod p to the m as well. So what he's saying is if you check all these congruences, a1, is it congruent to b1 mod p to the m? And then is a2 congruent to b2 mod p to the m? And is a3 congruent to b3 mod p to the m? And is a4, and so on. If you check these infinitely many ones, then what you win is one congruence. So by itself, it looks like a pretty out of context, like a pretty bad deal. And here q is just, as usual, e to the 2 pi iz. So we're just looking at a Fourier expansion here. But if you apply this to the weight 1 level 2K Eisenstein series. So with constant term, the Riemann zeta function plus higher order coefficients, the divisor functions. So here, we're just taking the sum of the divisors, raised to the 2K minus first power, divisors of n, and actually he has to apply this to the piece stabilization. So we're gonna stick a parenthesis p inside of here everywhere, which means we're gonna modify theta at p as follows. So now we have this modified zeta function 1 minus p to the 2k minus 1 and zeta of 1 minus 2k. So he applies these congruences, and what he recovers is Kummer's congruences and the Kubota-Leopold p-adic L function. So in particular, if we have 2k congruent to 2k prime, mod Euler phi function of p to the m, and p minus 1 doesn't divide 2k, then we have that our divisor functions, this is just a simple ring theory result using Fermat's little theorem or Euler's generalization to power working mod powers of primes. Mod p to the m. So this is a really simple thing you could give in a first course in ring theory for undergrads. But then what that tells us is that this result here, actually, these infinitely many congruences. These are simple to check. And then this tells us that we get that we get the Kummer congruences. Mod p to the m. And in fact, what Stair actually does is not just prove congruences, but put things into p-adic families and construct p-adic measures. I'm not going to use the language of p-adic measures in this talk, but that's really what when I say p-adic family, I really mean I'm really talking about p-adic measures. So we recover the p-adic zeta function of Leopold and Kubota. And this then inspired so now we've taken a step back. I so look at the earliest instance. This inspired further constructions of p-adic L functions. So the first one is what I just started with saying from earlier this week. So we're constructing p-adic L functions, interpolating values of classical L functions. So the first one of the p-adic L functions, interpolating suitably modified versions of these. So I'm not writing a superscript p and additional data, but when I write the L function here, I mean, it's p-adic incarnation. So the first thing we were just looking at was here the Hecke character. Of, well, we could look at a totally real field. That's what we just were looking at. This also, so this is done by Leon and Rivet. Also, though, there was work using Shintani's method of Kasu Nogues. To look at a CM field for half of all primes. Pat succeeded at this, and I'll just do it later, just in the past few years. Andreatta and Iovita extended this. So this is all happening. These early developments are happening right after Serre, so in the 70s, and this happened. This is like within the past few years, so much later development. Removing a condition on the prime P. Then you could ask about other things moving beyond characters. So you can look at a Rankin-Selberg convolution of modular forms or of Hilbert modular forms. And this was done by Hida in the 80s. In fact, so these happened in the 70s. This happened in the 80s in part because this recipe here, Rankin-Selberg, only, I guess Rankin had already in the 50s kind of worked out most of it, but I guess Shimura didn't really work out everything that Hida would need until the 70s. So the recipe didn't exist. This constant terms is what's getting used in the totally real case. If you look at Katz's paper, on p-adic L functions for CM fields, you don't see any constant terms, which might cause your stomach to drop because of the place where he's looking at the Q expansions and how he's approaching things, but he uses something called Damerel's formula, which turns out to be a special case of a much higher powered recipe, which was discovered in the 80s by Piatetsky, Shapiro, and Rallis, and is written in a book by Gelbart, Piatetsky, Shapiro, and Rallis, which allows one to extend this substantially further. So this is of modular forms initially and later Hilbert modular forms. So we could ask about automorphic L functions, possibly twisted by some character here with chi, and we always need an ordinary assumption for these results I'm putting down here on the hospital automorphic representation of, we could look at two cases you might look at. So this is just a standard Langlands L function. Are symplectic or unitary groups. So this was done for certain cases by Bricker and Schmidt, but done in full generality much later by Jing Liu. And so these, just to give you idea, these are in the 70s. This is approximately past few years, maybe about I don't know, 2019. They're, I think, revising that paper. So current. This is 20 in a paper in Jusu. And then myself and Michael Harris, John Chu Lee, and Chris Skinner also published a paper in 20 in Forum of Math Pi, a very long paper, 160 pages, and it follows this method. So it uses this so-called doubling method, as does Zhang Liu, and so we're using something about properties of Eisenstein series, and I should say that 160 pages is building on earlier work I did just on the Eisenstein series. So these things get quite involved. And in fact, if you even look down this list here, actually before delete and rivet, there was Coates and Sinnott for just the quadratic case. And these sound like they sound incremental. I don't think I even need to say kind of. They sound incremental, like somebody just has giving out a bunch of PhD problems and is like, now you try this case, you try this case, you try this case. Except when you look at like who did these things, probably these people had other things to do with their time than some little incremental PhD problems. And these first papers here, these papers in the 70s were all published in Mentionis in increasing length as well. So there's a lot going on in the background. It's not just a case of like, now Sarah's handed us this and we can just run and it's all done, but rather this is, I use the word inspired here to mean it tells us, hey, maybe we should try to do something with p-adic families. That became a very fruitful place to work, but there is a lot of work in the background at various stages, including even constructing the p-adic family of Eisenstein series. So what I like about this example, here is like it's familiar, it sticks in your mind, you can follow it quickly, you don't like, it's completely transparent, but it's misleading in the sense that you open any modular forms book and you're like, oh, there it is, or maybe there it is minus the p stabilization, when what's going into like here is really a lot of the Eisenstein series going into the later stages require a lot of work. You can't just like open a book and pull it out and see the congruence and everything. You do have to work quite hard. So that's what I'm going to be talking about in a bit. I also want to note that even these recipes here, especially this doubling, get just there's lots of technical stuff that has gotten worked out pretty recently, including I mentioned this paper in 2020. We at the time had only a qualitative description of the Archimedean factors, so the gamma factors, and it was just earlier this month, so in the past few weeks, that so Zhang Liu and I we wrote a paper finally computing those the Archimedean factors that were just mentioned qualitatively or conjecturally in here. We wrote a paper that just appeared in Prella online just, I don't know, maybe like 2 or 3 weeks ago. So there's a lot of stuff in the background, and those Archimedean integrals had been, like the computation had been open for 30 years, modulo Garrett having computed some cases under special conditions, such as requiring some data to be one-dimensional. All right, so for the rest of the talk, I want to talk about these. There's lots of different things that go in. I mean, you could talk about the Archimedean side. You could talk about families of automorphic forms that go into these recipes, more generally than Eisenstein series. But for this talk, given in the spirit of what the organizers asked me to do, I want to talk about a p-adic Eisenstein series on unitary groups. And why unitary groups? Partly because that's where, I mean, that's one of the places I've personally worked a lot on this, but also it's a good area for seeing lots of the kind of the general ideas that go into constructing these more broadly. So you know how to do the unitary case, you know how to do the symplectic case, and in fact, as a special case, recover the CM fields case. And when I wrote those Eisenstein measure papers at the end of my algebra number theory, when I actually have a section called something like relationship with Katz's work for CM fields that spells out explicitly how to get there. So it's a useful place to work. That said, if you only want to stick with Kappa characters, you should not it is way too high powered to be like, oh, well, this is a one-dimensional automorphic representation, so I'm going to do everything in the language, or the most general language is like, will create lots of extra troubles. And it's a special case, but that you can recover, but you don't need to, if you're only ever going to work with characters, you don't need to go to this setting. So, all right, well. All right, so. Yeah, Eisenstein series on unitary groups. And again, I'm not going to use the language of measures here, but that's what's actually lurking in the background. And again, this even though I'm talking about unitary groups, that in the way I'm going to present this talk, I'm mostly going to be presenting as much as possible, highlighting broader principles. So if you're like, I want to work on this, but I don't want to work with unitary groups or something, fine. You might also ask, why were we doing unitary groups, besides apparently it was something we could do because we had a recipe that was amenable to this. But unitary groups are also a really good source of Galois representations and close connections to GLN. So it's also beyond just, I mean, where you can only do the things that you can do that are doable with the machinery out there. But beyond that, it also is well motivated in terms of mathematically what we want. And maybe for one other question you might be wondering about, because we had a talk by Owen Potashnik about motives, and you might be like, why am I looking at this automorphic thing here? I want some like motive or Galois representation. I think we probably all do. But the state of the art currently is such that one of the main techniques we have is automorphic and through automorphic forms. So, all right, so here's our sort of key steps, and these steps are not going to say anything about unitary groups. I'll get into that in a moment, but just first thing that you need to do, and I'll say when I get into the steps a little more about how you might construct this, the construction does not, in spite of what you might think from Sarah's work, does not involve opening up a textbook on modular forms or automorphic forms on unitary groups. Well, a little bit, I guess, on automorphic forms on unitary groups, but it still involves substantial work. So you construct a C infinity Eisenstein series suitable for, so why C infinity? These are nearly holomorphic, which is not quite holomorphic, but retaining certain properties being holomorphic. So suitable for constructing your desired L functions. Why did we go to C infinity? We had this nice holomorphic thing here, and suddenly I'm like, oh, forget about that. Well, in these recipes that we have, this doubling method, for instance, or actually anything beyond this. So when you get past this case, everything below the L of S chi with chi, a totally real field, everything below where my arm is here requires working with C infinity Eisenstein series that can be obtained by applying certain differential operators to holomorphic ones. So these are holomorphic at certain points, and so you compute the Fourier coefficients where they're holomorphic. And then you apply to these holomorphic guys certain C infinity and their p-adic analogs, differential operators. These are Mas-Shimura operators, and more generally, Mas-Shimura operators in C infinity case, and in the p-adic setting, due to cats, to obtain C infinity and p-adic automorphic forms that are no longer holomorphic, no longer algebraic. These are p-adic things, in the p-adic case, living over the Augusta tower over, in this case, a unitary Shimura variety. If you want to just restrict to like the elliptic modular forms or Hilbert modular forms, then you'd be looking at a Augusta tower over modular space of elliptic curves or Hilbert Blumenthal abelian varieties. And just as a note, so if you've got some Eisenstein series here, and you apply a differential operator to it, and you put in a CM point that's ordinary, you also apply, so I'll just call these, actually, for this talk, yeah, I'll call it theta. So theta looks like, in the modular forms case, the Ramanujan's operator Q dBq. Maybe you have to modify this slightly, but there's a close, these guys are essentially equal up to some minor scaling normalization when you plug in an ordinary CM point. And this fact is really important for Katz's work on Type. This is really important for Katz's work in the attaching L functions to Hecke characters of CM fields. And in fact, it's the reason that he can't handle half of all primes. So he needs there to be ordinary CM points in his moduli space of Hilbert Blumenthal abelian varieties. And when the prime P is inert, that space is empty. And so he has nothing to work with. And what Andrade and Ubina are doing several decades later is extending that work. So finally, okay, so we've got some way to get between p-adic and C infinity things, and this has a nice action on in E here, in case that wasn't clear. This is our algebraic, holomorphic, nice coefficients inside of some ring that embeds both into the complex numbers and p-adic numbers so that it makes sense to whereas a ring that sits inside of C and sits inside of say, let's just look for it. CP, so that we've just put an embedding there so that it makes sense to compare these two sides. And finally, use the Q expansion principle, algebraic or p-adic ones. And p-adic interpolation of Q expansion coefficients to construct p-adic families. So at this final stage here, you're playing the game that we were playing back on that board with Sarah, where we finally got things set up, and we can now look and say, what do these Q expansions look like? When I said construct these Eisenstein suitable for constructing L functions, that's important because the goal is L functions. But in addition, they need to be suitable for computing the Fourier coefficients, for running through here, so we can talk about congruences, because otherwise, otherwise we're out of luck. You have an L function, which is great, but if you're interested in p-adic things, you can't run this program. All right, so I want to implement this for unitary groups. This thing here is just a general path, which you could say is getting applied anywhere below this line. So this is a lot of my, I guess, earlier work was focused on this. So G is going to be a unitary group here of signature. And N, regardless of what unitary group you want to work with here. So we have an ordinary cuspidal automorphic representation of a unitary, I should say, these are groups in case that wasn't clear. A group, this could be any signature, this could be any signature you want, but the recipe that we have requires embedding a product of two smaller unitary groups into a bigger one that's a signature. And then this contains inside of here a Ziegel parabolic. So this is a unitary group here, so it's a mixing a Hermitian pairing of some vector space V, 2n dimensional signature, and N over a CM field K. And just for this talk, to avoid having extra bookkeeping, I'm just gonna assume that this is quadratic imaginary, because I don't feel like having to carry around a bunch of embeddings. This Ziegel parabolic, this guy, you can choose your basis so that it ends up looking like this with a matrix inside of GLN. And we're going to take a section inside the induced representation from P of the Adels. The G of the Adels of a Hecke character times our adelic absolute value, which this thing we're going to view as a character on P via composition with determinant of just take the upper left. So just take that GLN in the upper left block, take the determinant of this, then apply the character. Here S for the moment is a complex number, and chi is a Hecke character. Of our CM field. And our Eisenstein series then is the sum f of gamma g, gamma in the few points of g mod p of g, so g here is in g of Adels, and just to be careful, I'll fix q bar into c and into cp. I'll take in okay algebra R. I'm gonna fix some integers k and nu. These are weights. I'm gonna construct a scalar valued automorphic form. If you're looking at modular forms, you have a weight k which shows, so you have like cz plus d to the k, which shows up in the power of the automorphy factor. When you're looking at unitary groups, you have an additional guy, c bar times transpose z plus d bar, an additional piece in the automorphy factor where you have to have a weight. So that's what the nu is here. And we have to take k greater than or equal to n for what we're going to do. First, I'm just going to give you a very rough theorem so you see where we're headed. And hopefully then when I give you the more precise one, it will be easier to make sense of putting into this context. So this was split between two papers they wrote in Krella and algebra number theory, and this gets fed as an ingredient into that work with Harrisley and Skinner. So the very rough, this is version. There's a p-adic family of Eisenstein series on G, E sub f of k nu. There's an additional, this is our k and nu, there's going to be an additional parameter, which I'll say something about in the more precise version, that varies p-adically as k nu and f very p-adically. Before I get to a more precise version, I just want to say that this thing is chosen to be, it's very close to Eisenstein series employed by Shimura in his study of L functions, except that data at P is tweaked, and that comes up in this guy F, which I'll say something more explicit about in a moment. And it's chosen so that the data at P is tweaked so that the Euler, so that we can interpolate things, much like how Sarah had to and tweak data at P, and you tweak the Euler factor at P in the L function that's showing up in the Eisenstein series. So this is maybe a bit too rough to feel like you have something to grasp onto. So a more precise version. Oh. Thanks. Star. So the general this rough version is just to convince you, okay, we're varying some stuff. And when I say vary p-adically, I mean the Q expansion coefficients will vary p-adically. And if you look at CM points, you can also vary things p-adically, analog with what Pat said, or really generalization, not just analog generalizations, it's to specialized factors. So we're now going to let F be function from okay tensor ZP across this is n by n matrices of ZP. This looks a little extra simplified here because normally you would have to tensor this with the ring of integers in the totally real field we're looking at, but because for the purposes of this, just for this talk, I have said I'm working over Q, I'm just tensoring Z. So there's just a little more in the background if you were to look at the paper. Let's look at a locally constant function supported on okay tensor ZP cross GLN. Again, you would normally have to tensor with your ring of integers in your totally real field, but because of our assumption, it's just Z for this talk. Satisfying this condition, norm A nu, there's this funny norm here, which I'll write down in a second. Vixen. It's Vixen embedding from K into Q bar. So two choices. Quadratic imaginary, just pick one. Sigma to the K plus 2 nu, and sigma bar to the nu for all E inside of OK cross. Again, there's not as much here if we're in the quadratic imaginary case, but you could more generally just don't want to deal with bookkeeping, work with the CM field. It's not necessarily quadratic imaginary here. So if you have this kind of F, then there's an Eisenstein series G sub K nu F on our group G. I guess this is unfortunate, but G is our group. The subscripts, it's the Eisenstein series. So I don't think there'll be any confusion. Of weight K nu. That means K is your usual CZ plus D to a power. There's just an additional term in the automorphy factors that you have to raise to something that's new. Defined over R. His Q expansion a cusp is of the form it is in some particular lattice inside a space of Hermitian matrices, and these coefficients here is a finite Z-linear combination of terms of the form F of A norm A to Q of A inverse beta times the norm, this funny norm K nu, A inverse that beta times determinant beta to the minus n when R equals C. This is the Fourier expansion. It turns out this function, this Fourier expansion of is we have an Eisenstein series holomorphic at k equals 2 of a C infinity form. This essentially this k nu s k nu f s holomorphic s equals k over 2. In case you're wondering, like, what is this F doing here? So F is encapsulating data about chi and other data you might want for your periodic L function. And I chose that notation and this formulation because it allows you to, if you're familiar with or unfamiliar with and just open Katz's periodic L functions for CM fields, it allows you to completely specialize to that case. And at the time I was working this out, I was very confused about what I needed or didn't need or what direction to go. And so the one thing I knew was that, well, GU1 is the Adele of the Adeles. This, the unit groups in the Adele is the Adeles. And so I knew that at least for n equals 1, it should be exactly what Katz does. And so it's easy to unwind from this, straightforward to unwind from this to recover Katz's result. And that's at the end of my section, end of my algebra number theory paper, illustrating explicitly. So just as a remark, you can use the Q expansion principle plus p-adic interpolation of these coefficients to put these into a p-adic family. So I just want to say a few words now about how to choose this guy F, because we have this general thing which I wrote down just because otherwise is where you're gonna get lost in what are these definitions, what is this big capital F, and so on. But how do you even choose one of these little guys F? Forgetting about p-adic things, just like where does it come from? How to choose F. So our section for our Einstein theories. And I should say, first of all, like anything in math, right? I guess the ideally you want to reduce it to things that have been done before. If we're doing p-adic L functions, I mean, somebody has proved, in this case, namely Harris and Shimura, have proved algebraicity. So there should be something out there giving us some, like we're not starting from scratch. And I said there's a recipe for getting L functions from these Eisenstein series. So somebody had to have already chosen F that's suitable for that. So it's not like we're just reaching into this space of induced representations and I'm like, I don't know, let me try this F, let me try this F. Didn't it, like there's a lot out there to inform you what should work. I should say though, when I was doing when I was doing this, I was a postdoc and I didn't when I look at it now, it's very clear to me why the choices work, but somehow, like I guess is often the case in retrospect, you're like, oh, of course that had to be the thing. But at the time, it felt like it involved more thought than I feel like with my perspective now it should involve. So I don't know why I have a 1 here. This isn't going to be in enumerated steps. Okay, so we're going to choose F. First of all, informed by work of Shimura, we're going to choose it actually to factor. And just because I'm assuming we're just doing quadratic imaginary extensions, so our base field's Q, I'll just write L for primes over just for rational places. So I have F sub L inside of induced representation. It's working locally here. Why I do this? Well, thanks to work of Shimura, this gives us a, well, okay, so there wouldn't be enumerated. There's 2 reasons. Here, I'll enumerate those. So the Fourier coefficients of the Eisenstein series associated to F, E sub F, factor over L as basically as a product. So if I look at the coefficient C of beta from up there, it actually factors then as a local guy, C sub L of beta, where this guy only depends on your choice of the local guy F sub L. And 2, only F sub L contributes for our L function to the Euler factor at L in the corresponding L function. So this just gives you more local control. And most of the time, that's not so important because, again, there's already some things done with this F. So ideally, you're building on what people have already done. But at P, it's really helpful to be able to zero in on the prime P, the one that you're actually interpret the P in the p-adic. So it's giving you just more control. And this first part's due to Shimura, and the second is what shows up in the approach of Gelbart, Piatetsky, Shapiro, and Rallis in the book of Gelbart, Piatetsky, Shapiro, and Rallis in the doubling method. These are both useful as you want to do things periodically because, well, you're going to need to be able to say what that Euler factor is at the end. And you want to make sure, like, you want to be informed by kind of your application to L functions. But this is also, of course, just useful if you're trying to see what your coefficients are, to be able to write them as some like product where you can deal with pieces separately. So what do these pieces look like? So at infinity, I've been writing things in terms of the group, but I'm going to write them in terms of symmetric space for the moment, just because that's probably the format in which people think of canonical automorphy factors. So at Archimedean places, which for us is only 1 right now because our base field is just Q since we're dealing with quadratic imaginary extensions. These are just built from canonical automorphy factors, which for us, at least if you write things in terms of your symmetric space, look like one of these, except there's a matrix here now. So you have some determinant. These are our weights K plus nu, and then there's an additional piece, C bar transpose ZD plus D bar. I'm just writing this to give you the shape of it. The main thing you should take away is they're built out of canonical automorphy factors, which is what would happen if you were working automorphically for GL2 or anything else. Just that this isn't some infinity, you're not picking some weird thing. You're picking the natural thing that you would see if you work with this in any setting. And thanks to some computations of Shimura, then the Fourier expansion coefficient is the determinant of beta, so this beta indexing things there, raised to the K minus N. At P, oh, and I just want to pause here because they said you also care about keeping in mind the Euler factors. As I just noted, we only had qualitative statements and also information due to Garrett about what the Euler factor is precisely where the Archimedean places in under very specific conditions. So this is the thing, like you have to keep this in mind, assuming you have this available. So we had some qualitative information about the Euler factors, but that's this work of Zhang Liu and me that was just published in Carla, like online, the head of print version within the past few weeks, this month. So so this is some guy related to F, but not quite equal to F, that goes into building F from the capital F from the more precise version of the theorem, given a locally constant subject to certain conditions, there exists some guy at P whose local Fourier coefficient is F tilde of 1 transpose beta. And the key input here is we want to control things at P, but often if you have something nice, then when you compute a Fourier transform, like you get, you just get something, but we need to know what and I'll be done in 1 minute. Or you're moderating, I will. You need to have some way to control things, so you also get a nice Fourier coefficient. And so there's this idea of cats to use something called a partial Fourier transform, which gives you a way of controlling what your Q expansion coefficient looks like, which is super important at P because we want to interpolate. And finally, at L not dividing P at infinity, these are built via essentially by translating, I should say, or adapting a recipe of Shimura from certain lattices, and we get just putting all of these guys together for all the primes not dividing P infinity, we get the result, so the product of certain, the values of certain polynomials where here, P sub theta L is a polynomial with integer coefficients congruent to, or sorry, not, it's identically equal to 1 for all but finitely many L. And you plug these in together. These guys, it's easy to see how to interpolate this stuff because you've got some character you can put in a p-adic family. Here with these guys, you can just use the congruences analogous to Serre. The F's get put into a family, and it's again easy to interpolate that guy using Fermat's little theorem or Euler's generalization. And I just want to say something about well, maybe in the interest of time, I'll say you can ask me about it after. But these polynomials here, maybe like, what are they? In general, they've not been computed in general, but for low rank groups, including n equals 1, they have been worked out. When n equals 1, you are almost working with a modular form in this case, or if you were to work with a more general CM field with a Hilbert modular form. So the sorts of thing that we're looking at, our Hermitian symmetric space is either just going to be upper half plane or a product of upper half planes. So we're used to from modular or Hilbert modular forms. And in that case, these polynomials end up being, like, maybe I will write these down just so you're satisfied with something that is, you can put your hands on. So in the modular forms case, so this is essentially n equals 1 with some mild tweaks. In that case, we have, so we're looking at unit system integer. These are Hermitian, this is a lattice in space of Hermitian matrices now. And in reality, we take them to be positive definite. So that means greater non-definite, which means greater than or equal to 0. So we're not negative integers in there. This guy equals 1 plus x squared plus dot 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 plus x to the d with v equals the order, the L of m. M's are beta from before. And so when you smash this all together, that tells us then that m to the, we had a det beta, just becomes beta, which is m for us. K minus n is 1. So we have m to the k minus 1 times, forget about the stuff at p for a moment. If you just multiply this times the product of these guys now, L to the negative k minus 1. What is this? This is just another way of writing the divisor function. You're going to get a sum of the k minus first powers of the divisors. And we had some fancier divisor functions in the work of, or in the talk of Mahesh, where he was working just fancier. Fancier just means more bookkeeping because it's Hilbert modular forms. You're going to get the analogs of those. And so secretly what we're seeing in the background is the same thing we saw in that, not secretly, I guess, but maybe it's just hidden in the course of an hour-long talk. We're seeing in the end kind of what we saw with Sarah. We don't see we don't see a constant function with an L function. You should go through recipe for that. But the other coefficients are really just really jazzed up divisor functions that when you go down to low rank are literally divisor functions in the usual sense of that word. So I'm gonna stop there. And if you have questions, you're welcome to ask me. If you want to see details about these things, everything I was talking about today is published and is linked from my website or the journals. Thank you.
Thank you, Ellen. Are there any questions for a speaker?
Yeah, so